Okay, so last module of this chapter is the concept of scalars and vectors, quantities. All right. So the first thing we're going to do is just discuss some scalar and vector quantities included in the syllabus, which is and their concepts. So scalar is something that only has magnitude, and vectors are magnitude plus a direction. So they are applied at a specific direction, and we need to consider those directions when solving problems which involve vectors. So first, let's discuss the easy ones, scalars. So the first scalar is time. Obviously, time goes in only one direction, and we don't need to tell that direction every time. So we just tell the time. Speed is also something that we don't need to tell the direction about. It's just a magnitude, and we are not concerned with the direction. Same as with the distance. Power, energy, you can even say energy is a vector because scalar, I'm sorry, because obviously you never say energy applied at this direction, you just say energy applied. Now let's move on to vectors. Vectors is something that has direction, velocity, displacement. Current has a direction. Forces are obviously have direction. Work has direction. Work done in a specific direction. So these quantities will always have a direction, and it's okay if it doesn't make sense right now, because we're going to do some problems and some more concepts, and you will understand vectors better there, right? So first we need to learn how to add and subtract coplanar vectors. So let's consider the first diagram here. Consider this box, and a force of 5 Newton is applied here, and a force of 3 Newton is applied here. So what's going to happen to this box? This box will experience a force of 2 Newton in this right direction, right? Because a 3 Newton force is pulling it backwards and a 5 Newton force is pushing it forwards. So the result would be forward minus backward, which would be 2 Newtons here. We can do more examples here. For example, this example here is almost the same, but in this case, what's going to happen to the box? It's going to move 8 Newtons to the right, experience a force of 8 Newtons to the right. Why? Because there is no backward, there is just forward, right? So forward plus forward is equal to 8 in this case. And this is basically most of the idea that you need to have when to add and when to subtract forces. So another concept that I want to give you is to consider vectors in negative, is to assign vectors basically a direction and give it a sign. For example, let's go back to this problem. A force of 3 Newton backwards and a force of 5 Newton forward. Now we can consider this, let's just make a graph. Positive x-axis, negative x-axis, positive y-axis, negative y-axis. But there's no forces in the y-axis right now. So we're just going to consider the x-axis right now, but we can also apply the same concept to y-axis. So let's just let's just assume this box is this dot here, and a force of 5 positive Newton is applied here, and 3 negative is applied here. Negative is applied here. So that is why we previously minus added a minus sign here because this 3 is actually a negative 3 because it's in the backward direction. We have to assign these values ourselves, and you can say that you can just say you can do it the other way around as well, right? And I'll show you how to do this. So this is 2 newtons to the right because we have assigned it's a positive 2, and we have assigned the positive value to the right side, so the 2 newton would be on the right direction. We would know it this way. Okay, let's do this backwards now. Let's just assign these values, and you can always assign this positive and this negative, right? There's no repercussions that you will have to face by assigning this simple the values that you're accustomed to, but I'm going to show you that it works backwards as well. So let's just say this is the negative axis and this is the positive axis. Now this is the box, this is the negative 5 Newton force, and this is the positive 3 Newton force. So in this case, 3 Newton positive and this negative 5 Newton force, and the answer would be negative 2 Newton. But look, now we have we've put the opposite values on the direction, and the answer is also in the opposite direction. So what have we assigned the negative value to? Right? So we know 2 newtons to the right. So you can assign positive and negative values to right or left as you want, but I recommend that you just use this Cartesian plane type plane because it's just what you're accustomed to throughout your O levels, and it's just easier this way. But you can do it the opposite way as well, and it always works. Yeah, unless you put some sign wrong, it always works, right? So the concept of coplanar forces is also something that you can keep in mind, but it isn't necessary, because they always give you coplanar forces, and coplanar means they are on the same plane, right? They are 2D forces basically. They will always give you 2D forces and not 3D forces, and that makes it easier for you to calculate. There are just a few things you need to keep in mind, and we'll keep calculating these vectors even in kinematics, so you'll get pretty good at this. So don't worry if this seems a little bit daunting right now, but because it's not. So the last part is representing a vector as 2 perpendicular components. Okay. Before that, I want to teach you head-to-tail diagrams. I'm sure you have seen these and you all probably already know this, but I'm just going to go through it so all of you understand what I'm talking about. So basically we have understood how to add forces either in up and down direction and right and left direction, right? But now what if we have a force in one in vertical direction and one in horizontal direction? What are we going to do? So first you need to keep an eye on this arrow and this tail. This is the head and this is the tail. Now what you want to do is first draw any force you want. Let's just draw the horizontal one, and I can show you what happens if I draw the vertical first, and the answer remains the same. So so we drew this here, and now from its head, right, its head to tail. So from the head of the first one, the tail of the second force starts. So just like this, the tail of the second force started with the head of the first one. So its tail is on its head and its head is here. So now we have both our forces, and the resultant force is like this, and a full triangle is made, and the resultant force is in this direction because it's going to the right and it's going upwards, right? So right and upwards, this is the direction of resultant force. And even if we do it the other way and draw the vertical force first, let's just try it, right? Upward force, and from its head the horizontal starts, and now the resultant is still in the direction this one, right? resultant R. So this may look different, but look, R is actually in the same direction, right? Let's do another example when the object is in equilibrium. So equilibrium, let's study equilibrium. So right now you don't need to understand equilibrium much because it's in the other chapter and we're going to go through it. But the only thing you need to understand right now is forces are balanced. Right now this is enough for you. So forces are balanced. What does it mean? This box again, 5 Newton here, 5 Newton here. So it's all balanced. Its vertical forces are 0 plus 0, which is 0. And its horizontal forces are 5 plus minus 5 because it's in the opposite direction. Let's say the left one is negative and it's 0. So both horizontal and vertical are 0. So this is in balance. This is balanced. So the system is in equilibrium. It is said the system is in equilibrium. So let's just discuss what happens when you need to suggest the resultant force. Basically, not the resultant force, the third force needed when one horizontal and one vertical is being applied. Because no other force needs to be applied here. It's an equilibrium. But when two forces are being applied in different direction, it's a whole another story, right? So let's just see. So this is force 1, F1, and this is F2. So again, we're going to draw the head to tail diagram any way you like. I'm going to draw horizontal first. This is F1 and this is F2. So this is the resultant force, right? So what is resultant force, right? Resultant force basically means that F2 is here and F1 is here. So it doesn't move like horizontally first and then upwards second, right? It moves horizontally and upward vertically basically together. So it moves kind of in this path, and the resultant tells us this, right? This is the resultant force. It tells us that the box is going this way, but we need to put this system in equilibrium. So if I apply a force here, R prime, let's just call it R prime because it's in the opposite direction of resultant force. So basically someone is pulling the box from the top direction and the bottom direction. The effect of these two forces is this way. So to keep it in place, I want to apply a force just opposite of the resultant force. So I will apply it here, and this would be in equilibrium. So the triangle would be something like this. You can see that this triangle is actually a full head to tail diagram if you see properly. So basically, if any MCQ or any question asks you if this is in equilibrium, you will always say yes. Why? Because no heads are colliding. But if it's not in equilibrium, a resultant would be like this. When you do MCQs with your topicals, this will all seem very easy after a few MCQs. So make sure you do your topicals and understand this concept well. Now, the last concept is representing a vector as its components. Now, we have understood that these two forces creates a force like this. Sorry, I can Now you have to note that I'm just saying forces here, but it can be velocity, displacement, or anything else. I'm just using the word force to represent a vector. Just as an example, this can be any vector. So just do keep this in mind. So these two forces are this. We just discussed this, right? Resultant is this. So that means that a force like this can be written as this, right? In exam, if they give you a force like this, you have to know the magnitude of these two forces, and I'm going to tell you how you can do it. So for example, here is a force at a 30-degree angle, and the force is of 10 Newton, right? So now, first what you have to do to solve any question, now this force is not, what is this force, right? It's neither, you don't know what the value of horizontal is and what the value of its vertical component is. To solve the problem, you will always need to know what the vertical component is and what its horizontal component is. And to solve this, you just have to apply the trigonometric ratio. So 10 Newton multiplied by sine 30, this is the value of vertical component, and 10 Newton multiplied by cos 30. Now the force, the component that is right opposite to the angle, which is the perpendicular of the triangle, would always have sine and the angle, and the component that is the base of the triangle will have the cos. And you can see this basically and these two ratios, right? You can apply these by yourself if you don't trust me, and this would yield the same answer. You can okay, it's just an assignment for you. You should try this. You should try this by yourself, and prove that this is 10 sine 30 and 10 cos 30. And it's easy, just apply this trigonometric ratio that I'm sure you already know from your O-levels or whatever maths you did in 10th grade. So now this is something that you would need a lot, right? To solve kinematics problems, you are going to need this a lot. So do go through this exercise and do make sure you understand this concept very well, okay? And now we're done with this first chapter. 10 more to go, and good luck for your exams or whatever. And I'll see you in the next video. Thanks.